In this video, we'll discuss batch normalization. In particular, we'll do an example of batch normalization, we'll discuss batch normalization in PyTorch, and we'll go over some of the reasons why batch normalization works. So here's our standard picture of a neural network, and we're only going to look at the case where we apply batch normalizations on the activations before we pass it to the activation function. So let's take a look at the first layer. So we have the outputs for each of the neurons, and what we're going to do is we're going to calculate the mean and standard deviation or variance for a particular mini batch. We're going to normalize the outputs, then we're going to scale and shift them, and these are actually parameters which we're going to learn via training. Then we'll take these outputs and pass them through the activation function. So let's do a little more concrete example. So we have our first mini batch, which we'll denote by the matrix or tensor x1. And then we'll have the output for the activations, which we'll store in the following tensor or matrix. So we'll have the output for the first neuron, second neuron, and third neuron. And the first sample will correspond to the first row of the matrix or tensor Z. And we'll use the same convention for each of the samples. And we'll just use the index m to represent the actual sample. So what we're going to do is calculate the mean and standard deviation for all the samples for each neuron, and then we'll normalize the output for each neuron. So here's our graph. So we'll calculate the mean for the output for the first neuron by simply calculating the average of all the samples, and we'll repeat the process for the standard deviation. We'll repeat the process for all the outputs of the second neuron and for the third neuron, and then we'll normalize the outputs. So the outputs for the first neuron we'll simply normalize by subtracting the mean and dividing it by the standard deviation. And just to note, we'll add a small little value in case the standard deviation is 0, which is in this case. So we'll normalize the values and we get the following values. We'll repeat the process for the second neuron, and all the ones stay as 1, and you can verify this by calculating it yourself. And all the zeros get converted to -1. And we'll repeat the process for all the outputs for the final neuron. Then we'll apply the scale and shift parameters to each of the neurons, and again, these parameters are learned via training, and this gives the model some flexibility. So in this example, we'll use the following values. So we'll take the output of the first neuron and scale and shift all the values using this transform. Same for the second neuron and the third neuron. Then we'll repeat the process for the second layer, where we'll calculate a mean and standard deviation. We'll normalize the values, we'll apply a second scale and shift parameter, and then we'll pass it to the activation functions. Repeat the process for the next batch. So we did for x1, so now we'll have the second batch, we'll denote by the matrix or tensor x2. We'll calculate a new mean and standard deviation and normalize it accordingly. And we'll repeat the whole process again, and we'll do it for the second layer as well. So now let's see how to make a prediction. So for the training, we'll calculate the mean and standard deviation for each batch as follows. But for prediction, we use the population mean and population standard deviation. And there's several ways to do this, but this is the most simple ways. You can see the PyTorch documentation for other ways to calculate it. How the prediction actually works. So the procedure is pretty similar. We take our actual activation functions and we apply the same procedure. And as you can see, the mean and variance in this case don't have the little batch term. What we do for the second layer, it's pretty much the same process. And of course, these parameters we obtain via training. So now let's discuss how to do batch normalization in PyTorch. Custom module or class neural network, and we'll create a batch norm object over here, and our input is simply the number of neurons for that particular layer. So in this case, it will be 3, and for this layer, it'll be 4. So we simply apply the batch normalization function to the output of that layer, and it'll perform the normalization, take care of all the training. And similar for the second layer, we'll do the exact same thing. So to train the model, it's pretty similar. And like dropout, we'll have to set the model to train. So here are the results. And just to note, we have to use model.evaluate to make a prediction. If you look at the training loss, you can see it converges a lot faster. And similar results for the test data as well. So let's discuss why batch normalization works. And we're going to only go over the methods we discussed in this course. So here we have an equation, and we have z1 and z2. And in this example, the results are constrained from 1. And in this results, variable z are constrained from 0.1 to 10. So if we look at the possible values for this equation, you can see that our parameters take on relatively equal values. And if we look at this equation, we can see the parameters have all kinds of different values they can take. So this expresses itself in the contours of the loss function. So we use batch normalization. In this case, we can see the contours are relatively round. So when we perform gradient descent, the steps are in the relatively same direction and it converges. And in this case, we didn't use batch normalization. And when we perform gradient descent, the gradients are pointing in different directions. So it will take us longer to converge to a minimum. So we also have the vanishing gradient problem, and let's say we have this sigmoid function, and we have these inputs. We take the derivative, and as you can see, these values are basically where the derivative is very small. Now, if we normalize the data, you can see that these values are in a range where the gradient doesn't disappear. So if you read the actual original paper from batch normalization, it discusses reducing internal covariance shift. We didn't discuss it because that's pretty involved, but that's another reason why batch normalization works. And they also said you don't need dropout in the paper, but you can verify that yourself. And it allows you to increase the learning rate. And finally, the bias isn't really necessary, and you can go over the math yourself to verify that. So that's it for batch normalization, and that's it.